Good morning, good afternoon, good evening, wherever you may be in this part of the world. Welcome to another session of my presentation series. And this time, the topic is electrical power generation utilizing solar photovoltaic energy. That's from solar energy. My good name is John Kwekwo Motu, and I've been a professional electrical engineer for the past 31 years, and I'm based in the United States of America. Now, let's talk about some logistics here. This is my YouTube channel, and the name is Work and Happiness, talking to the engineer. So this YouTube channel has tons of presentation material that you'll need as a development engineer, as an experienced engineer, mid-career engineer, and consulting engineers, and those that are interested in solar voltaic energy conversion process. Okay, so for you to be able to subscribe to my channel, you need to have a Google account. Very important. Okay, and if you like my presentation channel or presentation video, don't forget to like the button and share the knowledge. Share it to your friends. Okay. Okay, so this is also another slide that talks about what I just made mention in the previous slide. Okay, so this is the YouTube channel, and the name is Work and Happiness, talking to the engineer, right? Okay, so you need a Google account to be able to subscribe. And if you like my presentation, select the like button and share the knowledge. So now let's talk about the solar energy conversion process. What are all the pieces in bolting of the energy conversion process? Okay, so this occurs when solar energy is harvested from the sun. That is based on the orientation of the solar cell. And after harvesting, it is converted to a DC electrical energy. And if you need it to invert it to an AC, it goes through another process. The first stage of the conversion process is just converted from solar energy to DC voltage or DC current. Okay, so, and it consists of many solar cells, right? It's basically solar cells that are put together. You could have on a panel, you could have about hundreds of them, right, or thousands of them, right, depending on the size of the solar farm, to form modules. Right. Then, basically, many modules form together to form an array. So, the solar farm itself, the largest ones are basically an array of solar cells, right? And basically to harvest the solar electrical energy to produce DC energy. This should be solar energy. And after that, it passes through an inverter to generate the required AC power. If you want to integrate it to the AC grid, then you have to basically invert the power from DC power to an AC power equivalent. Okay. So, large solar farms are basically utility grade scale. Usually, the output or the rating is about 1 megawatts. Right? So those are considered very large solar farms, and those are built based on purchase agreement, and also has a substation, and also the SCADA system has meteorological equipment for weather prediction of wind, velocity, direction, humidity, ambient temperature. Now let's talk about the components of a solar PV plant. Okay, so this is basically the simplest, and basically it's the fixed. You can either have the fixed or the tracking. Okay, so the fixed basically has a tilt angle that is in one direction, right? Okay, let's say from 0 all the way up to 90 degrees, right? So it basically fluctuates between that range. On the other hand, the tracking one basically follows the sun. So wherever the sun goes, so if you have the sun here, right, it's basically going to rotate, you know, facing the sun, right? So that is called the tracking solar photovoltaic, right? Whilst the fixed one, the fixed tilt basically goes in one direction, like this. Let's say from here to here, and from it can also come from, you know, this direction to flat surface. Okay, so this is basically, you know, the solar panels that has been, or modules forming an array, and this is the equivalent of the array, right? And basically, you know, you have a DC power being generated, right? And it goes through the voltage that the DC is created might be lower, so it goes through a step up, right? Through a DC to DC converter that steps up the voltage to a higher DC voltage before it's fed to the inverter, right? Okay, so this is the inverter, and after that it goes through the step-up transformer, right? It goes through the step-up transformer, and right at the interface before it gets connected to the grid, you have mirroring. Definitely, you know, you need to mirror, you know, what you're selling to the grid, right? Then other controllers, you know, that allows you, you know, for the interconnecting utility to send set points, you know, let's say, and also curtailment, you know, let's say if they need to curtail the production of solar power, you know, so that, you know, basically, you know, you can go in an island mode. So there is a controller here that interfaces with all the plant equipment and also the grid as well, right? So basically on the SCADA, this is what you have. You have inverters, you have meters, you have meteorological station, controllers, IEDs and relays, transformers, right? So these are all the components of a solar farm, as you can see over here, right? Now let's talk about the different types of solar photovoltaic farms, right? Okay, so the first one, it's concentrated solar photovoltaic, or called thermal photovoltaic. Then you have the floating solar photovoltaic, right? Okay, so that one basically, you know, it's a solar farm that are basically floating on the surface. It can be either a river, it can be a lake, or it can be after flow of hydro plants, right? Then you have the traditional, right? You have the traditional one, and you can have the residential one and also commercial one. Okay, so the traditional one, you can have a utility grade, then residential, the ones that you find on the roof of your houses. Then commercial, it's the one that basically you find on commercial facilities, you know, like shopping centers and all those things. You can also have one in industrial facilities, right? Industrial facilities. Now let's talk about the processes of concentrated solar PV, right? Okay, so you have the sun over here, right? Okay, so this sun, basically, what is it doing? It's emitting solar rays, right? Solar energy. Right. Okay, so these, so let's give an example of a lineup of solar array of a solar farm that is basically on a hill surface, or a mountain surface, right? Okay, as you can see this. So these energy impinge upon the surface of this solar module, then it gets reflected back here. It gets reflected back here. to this mirror surface. So this surface is acting as a mirror, right? Okay, so think about this process, right? You have energy, solar energy that comes in here, right? Then it hits this solar panel. Then it gets reflected back here to this mirror surface. Then that high energy is impinged upon this, right? That goes through a lot of processes to increase the temperature of the harvested energy. And that energy that is increased, you know, it can go, let's say, from 500 degrees Celsius to about 1000 degrees Celsius. And that can heat water in a column to generate steam. Right? So you can have such a system in a hybrid system where you are basically cogeneration, right? You are basically generating electric power through a steam turbine. Then you are also generating electric power through the solar cells. So this can have a hybrid scheme or just a concentrated solar PV, where basically the radiation goes through a lot of reflection and basically impinging on the mirror surfaces, with the mirror surfaces very heated to basically increase the heating of the harvested energy. This harvested energy basically allows the increase of energy from 500 degrees Celsius to about 1000, which is basically able to heat a column of water and turns it into steam, and this steam basically flows into a steam turbine to generate the required electrical energy. This type of solar PV allows, basically is able to mitigate, you know, solar farms are able to harvest energy only when the sun is on. Okay, so at night when the sun is not on, solar farms cannot harvest that energy. It means that the battery energy storage system that basically store that energy has to come in place and basically support that delivering of electrical energy. But with this, you have that basically continuous cycle. There's no break in the cycle, right? During the day and at night, right, you have that continuous production of electrical power. There is no time that you have a curtailment of electrical power. That is the duration of electrical power is continuous during the day and at night, right? And that is for the concentrated solar PV. So this technology was invented basically to mitigate the drawbacks of solar PV, which basically is active and basically can harvest all the energy when the sun is on, right? So winter times and all those things, when the sun is not on, or the sun comes in, you know, in patchy or, you know, very, you know, micro weather, you know, then basically this becomes effective, you know, where basically it's able to, at a time, it's able to harvest the energy quickly, turns it into, you know, increase the energy through this mirror reflection surface and able to generate the required steam. And also it has different columns that is able to store that energy. Yes, and release that energy gradually. So, you know, there's a column that has a salt, a bed of salt that basically helps to basically harvest that energy and keep that energy and start releasing that energy when it is needed. Okay, so this is a, you know, much detailed picture of basically, you know, they say pictures are worth more than 1,000 words, right? Okay, so you have this is the sun, right? And the surface of the sun radiating all the energy, right? The solar energy. So basically, this solar energy hits the surface of the solar panels, right? And it gets reflected onto these surfaces, right? Okay, so you have basically this surface is acting as a mirror, you know, where basically it's able to increase the temperature from 500 degrees to 1000 degrees, right? As it heats the water that is in this column, right? Okay, so you have the solar energy gets impinged on the solar panels, gets reflected, right? So the reflection itself increases that energy until it hits these surfaces, right? And basically the energy is absorbed, right, through a reflection. There's a mirror surface that is here that basically also increases the energy further. And there's a tank of salt, like I told you, that is able to store that energy, right? You have energy increasing from 500 degrees to about 1000 degrees, right? So from here, then it goes through a steam generator, right? So basically, you have a steam generator, then it goes to a turbine, then the turbine is coupled to a generator to generate electric power, right? So this is what they call thermal solar photovoltaic. Right? So, and like I indicated, this helps you to mitigate the drawback that is associated with the traditional solar photovoltaic, which is active only during the day when the sun is on, and at night when the sun is not on, then this basically helps you to basically produce electric power continuously through the day and at night. Okay, so as you can see, this is a typical arrangement of the solar panels in a concentrated solar photovoltaic, right? Okay, so the solar panels are arranged at an angle, which basically helps with the impinging of and reflection of the solar rays, right? Okay, so it's basically impinges, then reflects back to the tower, right? Then basically increase of energy goes through that column until it creates steam in that column. Vertically mounted surface solar panel, which basically helps with the energy and reflection towards a mirror surface that basically increases the energy and gets reflected up to another surface where the energy is consequentially increased. Okay, so this is typical of the column that I was talking about, right? Okay, so you have all the solar panels, going all around, arranged in a circumferential, circular, arrangements. And basically you have the sun hitting on it, right, in different angles from different, and basically it gets reflected up here. Then basically the energy, basically the reflection, as it goes through the reflection, the energy is increased, right? And when it gets here, the energy is increased further from 500 degrees to 1000 degrees, right? So there's a column of water here, and in salt containment, the salt containment basically helps to retain that energy in the water, right? Okay, so basically this is a steam conversion process, right? That helps to create the steam. Right. Then from here, basically, it goes through a steam generator, right? It goes through a steam generator that helps to separate the dry steam. And the wet one basically gets to the bottom and flows back to another containment called water bed. Then the cycle completes. So the dry steam basically goes to the turbine, right? And spins the turbine. The turbine is connected to the generator and electrical output. So another picture of how this is generated. Okay, so as you can see over here, right, the solar panels, arrange all around it, and same process for the concentrated solar PV, right? Okay, so there is also another arrangement of the concentrated solar PV where basically the steam piping is basically integrated as part of the panel, right? You have water that flows through the panel so that when the solar rays hit the panel surface, right, it basically um, increases in energy and heats water that is in the piping that is basically integrated below the surface of the panel, right? So you have a series of connections of piping, and basically that becomes your steam piping that flows and goes through, a steam water separator, and the steam is harvested and it goes through a turbine. So there are different kinds of the concentrated solar PV. So now let's talk about the floating type, right? Okay, so as you can see over here, we have the floating solar photovoltaic, right? So the solar panels can be arranged in a column of water. It could be either be a river, a lake, or afterflow of a hydro plant, right? Okay, so what are the benefits, right? Okay, of this type of scheme, solar photovoltaic, right? Okay, it basically helps us. The water helps to cool the surface of the, below, underneath the solar panels, and it basically helps to increase the efficiency, right? And also, you are basically, making use of, basically, you are achieving a hybrid generation, where especially if you have a hydro plant and solar farm that is in conjunction with the hydro, you are basically able to mitigate because for a hydro power plant, right? Okay, during the dry season, right, the water gets dried up and the level of water basically goes down, right? Okay, so it becomes very difficult to maintain your base load, right? Okay, so that is when the solar farm comes into play, right? During the dry season, because during the dry season the sun is on, and basically you're able to harvest a lot of energy from the sun, right? And during the rainy season, that is when the solar farms cannot basically harvest a lot of energy, because the weather is cloudy and raining, right? And basically that is when the hydropower plant also comes into play. They have a lot of water in their dam or reservoir. So basically, you can have this hybrid scheme of power generation scheme, where basically they leverage the advantages of each other and mitigate the drawbacks of each other. Okay, so this is also another solar floating type of solar photovoltaic solar PV that is in a lake environment, right? So this one is a lake, right? And basically arranged nicely, and as you can see, the panels over there, right? Okay, so especially in congested cities, right? Okay, in urban cities where basically population has a lot of population, and also density, and also a lot of buildings, and there's no space. Space is a premium. Okay, so that is when you start utilizing this solar floating type of solar photovoltaic to basically leverage the amount of acreage that is available in this water bodies, and basically be able to generate electric power. Okay, so this is also an extension of the other picture, where basically you can see the fine arrangement of a river, and this one looks like a river, and basically this one is in a river environment, right? Okay. So basically, these floating type of solar PVs are able to be, they are basically anchored to the bottom of the river, the lake, or afterflow, right? And also anchored to the shore, the shoreline, right? So that is how they're held in place, right? And basically they float on floating bodies, right? Okay, so there's a floating body underneath it that helps it to basically float. Okay, so this is also another picture of it, and basically this one is on industrial facilities, right? Industrial facilities, and that is the afterflow of the industrial facilities, and basically they are making use of the land over there, and basically generating. So this one is a solar photovoltaic electrical power generation that is being used to support an industrial facility. And remember, I made mention that you have also floating solar photovoltaic that can be utilized in conjunction with a hydropower plant, right? Okay, so as you can see over here, this is a hydropower plant. Then basically, as you can see over here, this is basically the afterflow, right? So basically, this one, the solar PV, is located in the dam area. So as you can see, this is the dam area, right? And basically, it has to do with the high density of the volume of the water. The pressure is high, so these solar panels are able to float easily. So I'm pretty much sure it's because of the flotation. So basically, less material is utilized in their floating bodies that has to be put underneath, right? Because if you put it here, right, if you put this here, then that is the afterflow area, basically, forming a river channel, right? So that area, the volume of water is less, the pressure is less, so you have to put in a lot of effort, money, material in developing the required flotation bodies that has to be installed. So that is why you are utilizing basically the attributes of the pressure and the volume of the dammed area, volume of water, to be able to achieve all this. Okay, so this is a beautiful, solar floating solar photovoltaic that is formed in a circular motion. I think this one was based in somewhere in the Dutch line area. I think Holland area. And see how beautiful it forms. And basically this one is in a river. So basically, you see, they are utilizing all this acreage of land that is on the river bodies instead of locating them on land, right, where pricing is a premium, especially in cities that is highly populated, and buildings basically densely, so basically space and also cost of land is very high. So that is why they go to the extent of utilizing this water bodies to achieve this floating solar photovoltaic. Remember, I made mention about this photovoltaic panels are being held in place, right? Because you have it on top of a river, a lake. Yeah, definitely moving water body, right? Okay, so definitely it's going to move if you don't anchor it, right? Okay, so this is how they are anchored below to keep it in place, right? This is how they are anchored. Okay, so this also shows the how they are connected, the wiring and all those things. As you can see over here, even the wiring is also in basically a floating body, right? These are all the floaters, right? These are all the floaters, and there's a lot underneath here. These are all the floating body, right? Okay, that helps basically the connection, harnessing of the cables and all those things to be. And this is the inverter, and basically this has the inverter, the controllers, the SCADA controllers, and the step-up transformers. Okay, so this is an example of the step-up transformer, the inverter rather. Basically, what is the function of the inverter? The inverter basically helps to basically invert the voltage from DC to AC, right? Okay, so before that, you have this integrated transformer, right? That basically helps to step up the voltage to about 33 kV, right? Okay, so the voltage that is here is about 0.415 kV, and it comes to this step-up transformer that steps up the voltage from 0.415 to 33 kV. Right? Okay, so as you can see over here, and that is after the inverter. So the inverter has to invert this DC voltage to this AC voltage. Then it comes to this transformer that steps up the voltage from 0.415 kV to 33 kV. Then from there it goes to a substation, right? That steps the voltage from 33 kV to, let's say, about 132 kV or 230 kV. Right? Okay, so this inverter, in addition to step-up transformer, is also a floating body for a floating inverter solar photovoltaic. So this one is the traditional type of solar PV, and these are basically mounted on rooftop in basically residential. Areas. So as you can see, those are located right here. You can also have the commercial type, and basically commercial facilities. You can also have this roof-mounted solar farms. Right. Okay. So basically, some of these commercial facilities, they do that basically to cut down their electrical power charges, and bills that they receive from the utility, and at the same time, have the opportunity to sell back to the utility. Okay. So this one is a typical, traditional one, and this one is basically utility grade, right? Utility grade, and this is how they are mounted. So this one is basically the fixed tilt type. Right, basically you are able to rotate it all the way in one direction, right? Whilst the sun tracking one, basically, it's like they are mounted on an orbital. It's mounted on an orbital and is able to rotate following the sun all around. Yeah, so that is the difference between the fixed tilt and the tracking one. Another example of the fixed tilt type. Right, so as you can see, this is basically the pivot point, for it basically rotating in this direction, right? Okay, so basically, it goes from here to the side. Right? Okay, whilst, like I told you, the difference between the other one is basically the sun tracking one, it's able to move, in an orbital formation. Okay, so this is basically an arrangement of the traditional type solar PV. Okay, so this is another traditional solar PV, and basically, as you can see, the solar panels are vertically mounted, right? And as you can see over here, you have spacing in between these panels, and large spacing that allows hybrid performance of farming in addition to harvesting electrical energy from the sun, right? Okay, so basically this helps to basically the landowner, maybe he had some farm over there, and at the same time maybe unwilling to just lend their land just for solar PV, right? So basically, the investors can talk with the landowner, and basically, the landowner, they can basically go with this type of solar panels, vertically mounted solar panels, create the spacing in between, and for the farmer to plant, all those types, soybean and also strawberries, etc. Okay, so this is also another type of traditional type of solar farms, as you can see over here, and this is basically utility grade. And yes, sometimes, depending on the terrain, right? In certain countries, where there's a lot of mountainous terrain, right? And based on, basically feasibility studies is done to see, areas where there's optimum, sun, and especially, areas that have those, microclimates, right? Okay, so basically, feasibility studies is done to determine areas that basically we can harvest a lot of sun energy, right? So you find out that in these areas that on some hills or some mountains, that is where they are basically going to install these solar farms, in this stepped terrain. It basically, it's they are arranged like if you watch, it looks like a step. Okay, so this is also another beautiful picture of this solar PV located on the mountain, right? As you can see over here, and I've explained the reason why some of these countries that have mountainous geographical features, basically, leveraging is taken based on the optimum sun, and when the sun comes up and when the sun goes down, and basically the location of these solar PV farms are achieved. Okay, so this is a good picture of how during construction stage, how these solar PVs are basically installed, right? As you can see over here, right? The arrangement of the panels on these structures, and basically a lot of legwork is done, feasibility studies is done, and also lining up of this panel, through survey, it's all done, basically, before construction is starts. Okay, so this is basically a picture of the basic cell of what you see in the solar cell panel, right? Okay, so a panel or module has many of these cells, right? You can have about 1,000 cells, basically all put together, right, to form a panel. right? And basically or module, and from there basically different panels are connected together forms an array. So as you can see over here, right, the sun comes in and basically energy in watts, yes, energy in, energy out, and it's electrical energy out, and that is in DC, right, DC power, right, that has a voltage and current. Okay, so now let's talk about the solar cell, the cross section of the solar cell, right? Okay, so the solar cell basically consists of N-type. So this is a PN type semiconductor, right? Okay, so basically, from silicon, basically sand, right? Silicon. Okay, so basically you have the N-type that is negatively charged, and the P-type that is positively charged, right? Okay, so the N-type is doped with boron, right, to make it more negatively charged, right? Okay, then the P-type is doped with phosphorus to make it more positively charged, right? Okay, so in between that is a barrier, right? Because you don't want the negative and the positive basically to interact with each other, right? So you can see the barrier over here. So the electrons flow in this direction, and the positive ions also flow in this direction to achieve the required electrical flow. Okay, so there are different types of solar cells. You have the monocrystalline and the polycrystalline. The polycrystalline has many constituents, right? And they might be non-uniform, right? Okay, whilst the monocrystalline basically has very uniform components, right? So that is the difference in, and this one is the cheapest with low efficiency, right? And this one has high efficiency. As you can see, the efficiency of solar PV is about 20%, 20 to 25%, right? Okay. Okay, so as you can see over here, right? Okay, so this is the process, right? So from the solar cell, then you go to a solar module, right? This is a module. Then the different modules form a panel. Then different panels form an array, right? Okay, so that is the process, right? From cell to module to panel to arrays. All right, so an array of a solar farm is basically everything that is seen over here. Okay, so remember I did mention that there are two types of mounting, and you have the fixed tilt angle, right? Basically that allows you to basically rotate it in one direction, right? Okay, so they are very simple, and very cheap, require less maintenance, right? And basically, you have to determine the optimum tilt angle, and basically that will also be based on data gathered from the metro, right? And there's the other type that is basically, the sun tracking angles. Okay, so the sun tracking basically allows this to basically follow where the sun is, right? And it's able to rotate, on its axis. So you can have a single axis or the dual axis, and its goal is to increase the efficiency. So you're able to increase the efficiency for the single axis about 27%, and for the dual axis about 45%, right? So it's comparable to the fixed, that is about 20%. So see, and more of fact, some of them are even going to bifacial. So bifacial allows basically the sun also to impinge below that, and we are able to achieve about 10% more, to achieve about 55% to 60% efficiency. Now let's talk about the types, components of solar photovoltaic, right? Okay, so components. Right. So you have the wiring, right? Then you have the solar panels, the DC to DC converter. Okay, so the wiring basically, when you install the solar panels, right, it comes in cells, right? Cells to modules, right? Okay, so modules are all connected and all to form a panel, right? So these come in the form of a panel already from the factory, right? Okay, so you connect different panels utilizing different wiring. It's a lot of wiring, communication wiring, control wiring. Yeah, so you see a lot of wiring in this, communication, control wiring. Then basically power cables. So this will be integrated with the solar panels, right? Then, at the end, at each output of the solar panel, in the solar panels, right? Okay, so you have the sun energy converted to DC power, right? That voltage might not be high enough, so you need to go through a DC to DC converter to step the voltage up to a higher and required voltage to achieve the required AC equivalent voltage, right? Because for you to, the inverter has to achieve the required, so you need to basically raise the DC voltage a little bit higher, right? So you have the inverter basically that helps to basically invert the DC voltage to the AC voltage. So this one is DC to AC voltage. Then you have a step-up transformer, right? Okay, so after the AC voltage is achieved, right, you have a step-up transformer that basically steps the voltage up from 0.15 kV to about 33 kV, right? Okay, so this is basically different arrangements, right? We have you can have a centralized inverter, or basically an inverter dedicated to each string, right? Okay, so each string you have a combiner, right? It's combining all the DC voltage here, DC voltage here, DC voltage here, right? So you have an inverter here, inverter here, inverter here, right? Okay, so this basically helps to achieve different configurations of arrangement. Okay, so this slide basically tells us the wiring and cabling that is achieved. As you can see over here, this is the wiring and cabling. As you can see, you must see part of it that is underneath this DC, basically these panels, right? Okay, so as you can see, I indicated that it's a lot of wiring and cabling, and basically connecting from the modules to the combiner, right? And from the combiners it goes to the inverter, right? Okay, so from the modules or panels to the combiner, right? Panels to the combiner, then from the combiner it goes to the inverters, right? Then the inverters are basically invert the voltage to the step-up transformer to step up the voltage, right? So there's a lot of wire. Okay, so you also have a wiring and cabling that is for communication, right? Okay, so you have a fiber, then you have a internet cable, then you have a serial port. Nice. So different communication cables basically that helps with the control of the solar power plant. So if you go to a utility grade solar power plant, right, you can have this SCADA or part that has a step-up transformer, right? Then it has an inverter, then it has a SCADA system, right? And it has basically a meteorological, basically that helps basically provide data with regards to wind velocity, wind direction, and also humidity, ambient temperature, and basically projected information of any weather elements that is needed for the solar plants. Next is basically the inside of this SCADA communication panel, right? Inside it it's basically everything that you need to know, and basically connectivity to the inverters, right? Because you have a SCADA system, right? SCADA system is basically the centralized control, right? So this is integrated to the inverter transformer, any tracking system, Meteo, right? and any other communication system to the utility outside world. Then other, like I said, the solar panel itself. You also have the inverter, right? The inverter basically, its goal is basically to invert from DC to AC voltage. Yes, and at the point of interconnection, right, at the grade interface, right, point of common coupling, right? Okay, you need a mirroring, and you utilize the SCL. It's a typical one that they are using, SCL 735 for mirroring, so that basically the amount of power that you're sending to the grid, will be paid by the utility company. And these are, basically passive equipment. They are not active. And some of them can be revenue grade and non-revenue grade. Okay, so this is an example of a meteorological station, right? And basically gives wind direction, anemometer, wind speed, rain gauge, humidity, ambient temperature, and basically everything that needed for the solar farm. Okay, so this is also another picture of an inverter and a step-up transformer, right? So basically you have a DC to DC converter, right? That steps the voltage up to a required DC voltage, right? Then it comes into this inverter that inverts it to the AC equivalent, right? It's about 0.415 kilovolts, right? Before it goes to this transformer that steps the voltage up from 4.5 kilovolts to 33 kV. Before it goes to the grid step-up transformer that steps it up from 33 kV to 132 kV or 230 kV, depending on the voltage requirement of the interface utility. This is basically an arrangement of the integrated substation, and basically has a substation breaker, it has a step-up transformer. So this is the transformer that steps the voltage from 33 kV to 132 kV or 230 kV. Okay, so this is also another picture of connected grid substation, and basically it has a main transformer, right? Its goal is to step the voltage up from 33 kV to 132 kV or 230 kV or 345 kV, and has capacitance to support voltage regulation, and has a SCADA system, and basically the SCADA system has IEDs, controllers, and automatic voltage regulation. With that comes to the end of my presentation, and I hope you enjoyed this presentation. So if you enjoyed it, don't forget to like my presentation and share. And this is my YouTube channel. The name is Work and Happiness Talking to the Engineer. It has tons of presentation materials that can help you as a young engineer, aspiring engineer, mid-career engineer, experienced engineer, consultant engineer, and if you can subscribe it before you can subscribe, you need a Google account. Right? So for you to be able to subscribe to any channels and other channels that will be of interest to you. Okay, so with that comes to the end of my presentation. Thank you so much for your listening ears, and look out for more interesting presentations from me. And once again, thank you so much. My good name is John Kweku Amoto, and I've been a professional electrical engineer for the past 31 years, and I live in the United States of America for the past 31 years. Thank you.